everyone. Today I'll be talking about graph theory, which will be the topic of the fourth and final ACSL elementary division competition. Alright, so what is graph theory? Graph theory, to start talking about this, first we have to define what is a graph. And a graph, simply put, is a collection of vertices and edges. But what are vertices and edges? You can think of a vertex, which is the singular form of vertices, as a point. And you can think of an edge as connecting two vertices. So you can draw graphs by using these vertices and edges. So the precise way to define a graph is to say it consists of a set of vertices. So like some vertices which you give names, and the set of edges between these vertices. Not every two set of vertices has to have an edge between them. For example, say we have the vertices A, B, C, and D. These are curly brackets. Then if we have the following graph like this, so these are the vertices A, B, C, and D, then maybe we have our graph looks like this. So then the edges would be AB, AC, AD, 1, 2, 3, BC, BD, and that's it. Like that. This kind of graph is called an undirected graph. Because there's no arrows on the lines. So in our elementary division, we only care about undirected graphs. So you don't worry about this too much. So there's a special type of undirected graph called a complete graph. This means that there's one edge from every vertex to each of the other vertices. So the graph is completely connected. So such a graph would be the same as drawing a polygon with a certain number of sides and then also drawing in all of its diagonals. For example, a complete graph with 5 vertices would look like this. Where you can see that every vertex is connected to all of the other vertices. For a complete graph, we have the following formula. The number of edges equals the number of vertices plus the number of diagonals. here in this pentagon, we see there are five vertices, A, B, C, D, and E, and there's five diagonals, 1, 2, 3, 4, 5. Therefore, there are 10 edges. Now let's define another term for a graph, which is a path. A path is defined between two vertices, and it's a list of a list of all the ways to get between these two vertices. For example, BD would be a path of length 1 because you're only crossing from one vertice to another vertice. While B Well, ACB would be a path of length 2 from vertex A to vertex B, although you are stopping at vertex C in the middle. Then we have a special type of path, which is the path you'll most typically be working with, which is the simple path, where no vertex is repeated. For example, you might have BACBD is a path of length 4, but not simple. But it's not a simple path because the B is repeated. There's two B's. So the two examples above, BD and ACB, are both simple paths. Let's define another term, connectedness. A graph is connected if there exists a path from every vertex to every other path. There is a path from every vertex to every other vertex. This is different from a complete graph because it doesn't require that the vertices be directly connected by an edge. For a connected graph, you only need to have a path between the two vertices. For example, you might have this graph, A, B, C. And this graph is connected, but it's not complete. If you have the graph like this, then it's not connected or complete. Okay, let's define another term, which is a cycle. A cycle is a special type of path that is simple except that the first and last vertex are the same. So essentially, it forms a cycle back to itself. For example, ABDA is a cycle. In the following graph. There are also more than one way to identify the same cycle because you can list any of the vertices first. For example, BDAB is the same cycle as ABDA. Now let's define another term, traversability. Traversability of a graph refers to whether or not you can use every edge once and only once without lifting your pencil. Basically, can you draw the entire graph without lifting your pencil or repeating edges? If the answer is yes, then the graph is traversable. If you're interested, the Seven Bridges of Königsberg is a famous example of traversability. And you can search it up if you are interested in this. Okay, so this is overall all the information points that you need to know about graph theory. And next, we'll go into some practice problems. Okay, here's our first practice problem. Given the following description, list all of the edges represented using the first letter of each person's name. Do not include any duplicates. So we see that there's Amy, Ben, Carol, Dave, and Ellie. So there's 4 people involved in this scenario, which means we'll have 4 vertices. We can draw, 5 vertices, 5 people and 5 vertices. So we can draw it simply like this. A, B, C, D, E. So Amy shakes hands with Dave and Ellie. Ellie shakes hands with Amy and Ben. Ben shakes hands with Ellie, Carol, and Dave. And Dave shakes hands with Amy, Ben, and Carol. Carol shakes hands with Ben and Dave. So now we can list all the vertices, or you don't even have to draw the graph. You can just write it, but you need to make sure you don't include any repeats. So AD, AE. The best way to do this is to start from A and then go down the alphabet, and then once you're out of A's, go to B, which will help you not repeat. So then you have BC, BD, and BE. And then you go to C, you have CD. And notice you don't have to say CB because we already listed that here as BC. And for D and E, we see that we've already written all of the vertices associated with that. So we see that there are 6 edges that should be listed, and this is the correct answer. Let's move on to a next problem. For the given graph, identify the set of edges needed for this graph to be a complete graph. List them in alphabetical order. Okay, so we must recall the definition of a complete graph, which means that every edge, every 2 vertices must have an edge connecting them. So we just need to see which vertices are missing. We can draw them in as follows. A, D, B. So A is not connected with C, so we need that. AC. And then B, we have BA, BC, but we don't have BD. We also have CA, CB, CD, CE. We have DA, DB, DC, DE. and then we see E is already connected to everything. Therefore, the four listed vertices, the four listed edges are the ones needed for the graph to become complete. And this is the correct solution. Okay, next problem. If you are delivering pizza from location Q to all other places and returning to location Q when you're finished, how many different routes could you take? In other words, count the number of Hamiltonian circuits starting with vertex Q. So here is this Hamiltonian circuits, but what it really means is cycles, because it has to start with Q and end with Q. And you're also delivering to all other places. So you have to go to all of the other vertices and then come back to Q. So we can list these out alphabetically to make sure we don't skip any. And you'll notice that most of these graph theory problems involve listing something, so it's very important to be careful, take your time, and not skip over any cases, which is why going alphabetical is helpful. Going alphabetically. Okay, so we need to start with Q. Q, and then P is first in the alphabet, so we can start with P, right? So Q, P, and then there are several possibilities. You can go to R or you can go to S. So let's say we go to R, T, S. So then from R, you can only go to Q or to T. So you have to go to T because you don't want to go back to Q yet. So you have like this. Q, P, R, S, T, Q. And then again, you can go to P, and instead of going to R, you can go to S. Q, P, S. And then you can only go to T, R, Q. Okay. So these are the two cases with P. What if we go to R first? Q, R, you can go to P or to T. Q, R, P, you must go to S. Q, S, T, Q. Q, R, T, S, P, Q. Next, we can try going to S, Q, S. And now you can go to P or to T. Q, S, P, R, T, Q. Q, S, T, Q, S, Q, S, T, R, P, Q. And then we can try going to T, Q, T. You can go to R or to S. Q, T, R, P, S, Q. Or Q, T, S, P, R, Q. And since this is asking how many different routes can you take, you can count these up to get 8. Great, let's move on to the next question. Question 4. In the undirected graph shown below, how many cycles are there? Remember that cycles must include at least 3 vertices in an undirected graph, and it is a different cycle if it goes the opposite way. So again, this time we need to count carefully and make sure we don't skip any cases. And one way to do that is to do casework by the number of um vertices in the cycle. Let's start with the shortest 3-vertex cycle. So remember that a cycle must start and end with the same vertice. Again, we can go alphabetical order to keep track. We can do W, X, W, sorry, at least 3 vertices means at least 3 different vertices. So we want W, X, Y, W, for instance. Or you can have W, Y, X, W, which by the definition given in the problem does count as a different cycle. We can also do... No, that's it for the one starting with W. Now let's see what we can do starting with a different letter, X. Notice that we can't include W in any cycle starting with X because then it will only be the same cycle as the ones we've already listed. So we can do something like X, Z, Y, X, and X, Y, Z, X. And this is also asking how many. So here we have 4 so far. Now let's try the ones with 4 vertices. Let's start with W again. W, X. Can we do W, X, Y, Z? But then you can't go back to W. So we can only do W, X, Z, Y, W, or W, Y, Z, X, W, which there's 2 options. Now, since this cycle uses all of the different vertices, there's no more cases in this for 4 because otherwise it would just be the same cycle written a different way. And you can verify that yourself to check. And since there are only 4 different vertices, there's not going to be any cycles of length longer than 4 because a cycle cannot repeat any vertex except the first and the last. Therefore, you do 4 plus 2 equals 6, and that is the correct answer. Okay, let's do the final problem now. Identify the starting and ending vertices that must be used in order to traverse this following graph. If not possible, write none. So you can try this and write a few examples, but you might also know this, and I didn't explain it earlier, but traversable graphs must have an even number of vertices that each have an odd number of edges connected to it. And the only 2 vertices that have an odd number of edges connected to them are, you can try it out and list all of these. For example, C, F, and D, this has 3, so that's odd. And then D, you have D, J, or C, J, So this is 2, and then E is JH2. F is CJHG, that's 4. G is HCF, that's 3. H is JEFG, it's 4. And J is HFED, it's also 4. Then you see that the only vertices with an odd number of edges connected to them are C and G. And this will be the answer. And you can also see that this C and G can be in either order, so it doesn't matter which one you write first. You can also try it yourself to check if you can find a traversing path through this graph, starting at C and ending at G, or vice versa. That's it for today. Thank you for listening to this talk about graph theory, and I hope you do well in the last competition of the ACSL Elementary Division. Thank you.